Okay, this video is covering Z transforms, and in particular the inverse Z transform. Now I wanted to point out that when you take complex variables, you end up looking at how to do a contour integral in the complex plane, and it turns out the formula in general for inverting a Z transform is a contour integral over a certain closed region C, z to the minus n minus 1 dz. All right, and if you know the region of convergence, you can use this to actually compute the inverse Z transform. You might remember this as the residue theorem. But it turns out it's sort of complicated to do this, and so you did this back in complex variables, if you took that class. The residue theorem is something that probably comes to your mind from that class. But it turns out we're not going to do it this way. Rather, instead, we're going to use tables and because of the way things normally work out, you'll need to do partial fraction expansions to do inverse Z transforms. Okay, so this video covers inverse Z transforms, but also a bit about the convolution theorem. So we're going to start with an h of z. Let's define h of z to be 3 times 1 minus 2 z to the minus 1 divided by 1 plus 1 half z to the minus 1, 1 minus 1/3 z to the minus 1. Okay, it's got a pole, a finite pole. It's got a couple of finite poles and one finite zero. Okay, so in this particular case, what I want to do is two things. I want to find h of n, which is the impulse response. And for that, we assume the system is at rest. Okay. Assume 0 for initial conditions. And we also assume that the system is causal. Okay, in class we talked about regions of convergence, and if you're given that the system is causal, you no longer need that information from the region of convergence. You can just do the causal inverse. Okay, so that's what we're going to do. And then under the same assumptions, part B, I want us to find the step response. Okay, so the step response is x of n is a unit step. The impulse response is x of n is delta of n. Okay, so for part A, well, x of z, if you have x of n as a delta function, x of z is just 1. Alright, so our output y of z is the same thing as h of z, and so I rewrite that here. And if we do a partial fraction expansion, if we write this as a over 1 plus one of the pole terms plus b over 1 minus the other pole term we would be able to do this inverse transform because we already know what the inverse of each of the components would be. All right, so we simply need to find A and B. All right. Now you've probably done this many times before. In this particular case, we have distinct roots. If you have distinct roots, particularly real roots, then you can use what I call, or what a lot of people call, the cover-up method, which you probably learned in signals and systems. So let's go through this because there's a slight little twist on the cover-up method. It depends on how you interpret z to the minus 1 versus z. All right, so here's what I do. I know I want to find the coefficient a, and so I look at the denominator term, and I see, all right, if I want to set that term equal to 0, that happens when z to the minus 1 is equal to negative 2. All right, so I'm thinking about the whole quantity z to the minus 1. I don't solve for z. I think of z to the minus 1 as its own separate entity. Okay? So from there, what I want to do is multiply both sides of the equation by that denominator term. That's part of the cover-up method. Okay, so when I do that, I get 1 plus 2, I'm sorry, that's a minus, z to the minus 1, and I multiply by 1 plus 1 half z to the minus 1, and I divide by 1 plus 1 half z to the minus 1, and then I still have this remaining pole term. All right, so the idea here is that these two terms would actually cancel. All right, and I do the same thing on the other side, and sorry, I went too far with that fraction. And on the other side, the pole for the a term cancels, and we're just left with a by itself. That's what we were looking for with the cover-up method. And then for b, we have 1 plus 1 half z to the minus 1 over 1 minus 1/3 z to the minus 1. Okay, so this is an expression that should hold for all z. And so in particular, what we do is we let z equal minus 2, because that's where the root term happened from above. Okay, so when we do that, we plug in z equal minus 2, and what happens is the 0, there's a 0 that shows up in the numerator, which effectively we multiply b times 0, and the b term falls out. All right, so we're left just with a. All right, so I think you knew that already, but what we then get is we plug in these terms like I have shown here. We have this expression for a, and we can solve that a is equal to 9. For b, we plug in z equal minus 3. And in this particular case, what we do with b is we cover up this term. So we don't use that term, we plug into what's left. All right, so I show that here. For b, we plug into what's left. I notice also I do this little trick of multiplying top and bottom by 2. All right, so when I do that, this 2 here, oops, this 2 distributes across, and so when I look at this term, I have 2, this 2 cancels, so I'd have 2 plus 3, and on the bottom I get 5. So that's just a mental trick that I use to clear those fractions. All right, so you end up with the terms for a and b, which gives us h of z, and lets us write the final expression for the impulse response. Okay, in part B, we are looking for the step response. Okay, so for the step response, we take the z transform of x of n. X of n is a unit step, so the z transform is 1 over 1 minus z to the minus 1. We had derived that in class, and hopefully you can remember that. All right, or at least look it up in a table. So we have y of z. Because of the convolution result, y of z is x of z times h of z. All right, so at this point we can write down y of z. And we take the original h of z and you multiply that by x of z. All right, so when we do the partial fraction expansion, this expands to a over the first pole term plus b over the second pole term plus c over the term that came from the unit step input. All right, so we can use the cover-up method, and what we're going to do here is we're going to look at the root location for the denominator of a, and so my thought here is I plug in z to the minus 1 equals -2, covering up this term. All right, so I plug into what's left. All right, so when I do that, I have 3, 1 minus 2, z to the minus 1, but z to the minus 1 is -2. And on the bottom, I have 1 minus 1/3, plug in the -2, and then 1 minus, plug in the -2 here. Okay, so I've got that term. Again, I want to clear this fraction 3, so I multiply 3 over 3. Okay, so multiply by 1. And what I'm left with is, from this term I get 3, and then another 3, and then, I'm sorry, 5, and then 3. So 3 times 5 times 3. And on the bottom, because this 3 gets distributed through, okay, that would be 3 minus a -2, which is 5. Okay, so we get a 5 on the bottom, and then the remaining term is 1 minus a -2, which is 3. And so when I cancel terms, I end up with just 3. Okay. I do the same thing for the b and the c terms, so let me just show those here. So it's just a coincidence that everything ends up 3's on this problem. Okay. Once you have a, b, and c, you can write down the final result for the unit step response. Okay. And it would be 3 because that's the a term, minus 1/2 to the n, plus a 3 1/3 to the n from the b term, minus 3 from the c term, all multiplied by u of n. Okay, so this would give us the overall step response. Okay, so I want you to be able to do this on exams, in particular partial fraction expansion with real roots. Hopefully you can get pretty proficient at that and be able to solve that pretty quickly.